Okay, last time on Catboy Gravity, we did an application. So we appli- we applied our previous lectures in constructing some metrics um, for basically space times around a specific catboy, and this one was a prominent, or at least is a prominent YouTuber, or VTuber as a fanboy as well, and his name is Line Chu. So we constructed some space times for Line Chu, mainly the Schwarzschild in Schwarzschild form. Uh, so we did the Schwarzschild metric first, and then we did a conversion of coordinates or a switch of coordinates to turn towards a to convert that mass or misuse Line Chu's world sphere into creating an Einstein-Rosen bridge. So an Einstein-Rosen bridge. So also known as a wormhole, of course. And if you guys will punch the numbers, you'll find, of course, that the proper time that it takes to travel in that region of space-time, which we have converted from the Schwarzschild metric, if you travel through that tunnel, it'll actually take minimal um, s. Actually, it'll take minimal s in order for you to cross that Einstein-Rosen bridge. Now, in our conquest of misusing femboys to distort space-time, today we're gonna be discussing about some more metrics, and it's gonna become a bit more complicated than our usual discussion, because we're gonna discuss different coordinate um, systems and a different formalism for general relativity, which is namely the ADM ADM formalism. So, and if you guys are well versed in physics, and of course, maybe space-based or physics-based propulsion, maybe you guys will see where this is going. In fact, today we're going to be discussing a misuse of femboys into morphing space-time such that we achieve some form or analog of FTL travel, and that's to the Alcubierre metric, or as you guys know, the Alcubierre drive. And we're also going to be discussing a less spherically symmetric space-time, namely, instead of a world sphere, I consider a world cylinder of a catboy. So it's gonna be a wonky looking shape. It's gonna look something like this, um, and we're gonna have a different form of constructing it. So, yeah. So let's begin with my um, cylindrical coordinates. So in cylindrical coordinates, we only have, I mean, at least in the cylindrical space-time, we only have, well, of course, we still have four vector components. This is a four vector, a space-time four vector, but mainly um, these components uh, describe a point differently than we would using spherical coordinates or Cartesian coordinates. So we still have the same radial line r, um, and then we still have the same azimuthal angle phi, but instead of a instead of phi being over here and I have a theta over here, what I instead have is a z. And in fact, in your first introduction to general relativity, Professor Hughes used this type of coordinate. So you can think of it like this. So I have my cylinder. So it could be a unit cylinder. And then I center my coordinate system. And then this is my r. And then this is my z. And then the angle it makes, so it's a bit hard to see, but the angle over there it makes is phi. So that's my cylindrical coordinates. Just so you know, it's still an orthonormal basis, but I didn't say this at the beginning of the course, but we will not necessarily be working in an orthonormal basis all the time. So, what is the name of the space-time associated with a spherical catboy? So first, let's create a procedure. First, we need a procedure on how to actually construct um, such a celestial object. So, right. So, this time we still have the same parameters. We still have the height of my catboy. So height of catboy, and I still have their mass m. Mass of catboy. So the same parameters, but instead, what I do is I set r equal to h, and then the mass, stays the same. And yeah. All right. So r equals h in this case. And so instead of revolving r around all axes, I'm just revolving it around the z-axis. So just around here. And then the resulting circle I slide it upwards. So I slide it upwards, or consider, so if my base circle as base is the set of all numbers x squared plus y squared equals h squared, such that x, y, and h are in the reals, or some Lorentz invariant scalars, then what I'm doing now is I'm multiplying SB by R, or a Lorentz invariant scalar. So this just gives me the topology of the space-time I'm considering in this metric, which we call the Levi-Civita or Levi-Civita space-time. The Levi-Civita metric. So this is the topology of my space-time. But what is the metric itself? So this is actually different. There's a general form of the line element, and the general form is the following. That is ds squared is equal to minus f dt squared plus exp of mu dr squared plus dz squared plus L, I'll pick this type of L d phi squared. So that's the line element of my metric, a general line element of a metric that concerns a Levi-Civita spacetime. So F, mu, and L are all functions of R. So that. And just so you know, R is not to be confused with, I guess you could say it's set to H, but it's an arbitrary value because we're considering a family of catboys. We're not just considering one catboy. So that. Now, a particular form of this metric involves the diameter of a base of your cylinder. So if you guys know the radius, of course, the diameter is simply 2r. So this particular form of the Levi-Civita spacetime is given by this line element that is precisely r to the 8 sigma squared minus 4 sigma times dr squared plus dz squared plus d squared, the diameter squared, r to the 2 minus 4 sigma d phi squared minus r to the 4 sigma dt squared, where sigma is also another constant and d is the diameter. So this is a much more, I suppose, closed form, or form that you can use to actually describe your cylindrical catboy. So there. So any answer or any solution to the Einstein Field Equations that are only cylindrically symmetric must take on this form over here, in the form of the Levi-Civita spacetime. So Levi-Civita spacetime. Now, all right. So, in our study of physics, especially because, of course, before you study general relativity, it's assumed you're experts in special relativity. So, right, we know from special relativity that the speed of light is constant, right? So, in a space-time diagram, so is my x, and this is my t. Or no, this reverse it. This is my x, this is my t. As time goes on, light spreads out by a 45-degree inclination. This is 45, 45. And we all live in the region within the light cone. We can never escape the light cone. To escape the light cone is to travel back in time, or if I want to escape it, I want to travel at a much steeper inclination, which means I will have to travel faster than the speed of light. But as we all know, nothing can travel faster than the speed of light. It will require infinite energy to do so. And so, what are some ways that we can sort of cheat? How do we cheat our way into traveling faster than the speed of light? Of course, there are very practical applications of this. For one is, how do we transport our femboys from one star system to another system without them aging and dying before they even get to their destination? So, how do I achieve faster than light travel within the confines of general relativity? And one solution was proposed by a physicist, Miguel Alcubierre. So Alcubierre. It was proposed, I think it was in 2000 or in the 90s. What he did was, instead of, alright, so I have two reference frames. So instead of considering one reference frame, we're in the spacecraft. So I have one reference frame over here. I have one IRF of my spaceship. Let's say this is my spaceship full of femboys. So it's my spaceship full of femboys. And then I accelerate it. Right, that's the usual way of traveling to places. We accelerate a single reference frame. And we know that the reference frame cannot travel faster than the speed of light. So what if we consider two inertial reference frame? So one reference frame here in our spaceship, and I have another reference frame here that's not in the spaceship. And now what I do is encase the first reference frame with a bubble, and then what I do is the space-time in front of the ship, I squeeze it, basically. I squeeze it, and then the space-time behind the ship, I contract it. So this is what Alcubierre proposed. And you'll find that for the reference frame, so the IRF, inertial reference frame outside the bubble, we'll see that by the contraction and squeezing of the space-time around this first inertial reference frame, the first inertial reference frame is actually traveling faster than the speed of light. And it will get to that star system, the distant star system, in practically no time at all. And what exactly is the form of this metric? Well, I suggest you guys just look this up, because this is going to take me more than an hour to discuss. But I believe there's a Wikipedia article on it. It's called the ADM formalism. I stated in the beginning of this video, and this metric employs it. So what we're actually considering is hypersurfaces, so higher dimensional surfaces, that squeeze and stretch, and these are actually part of our space-time. So the look of the metric is something like this. It looks a bit hard to describe, but it should look like this, basically. So this is what space-time is visualized to look like. So there's a bulge here. Uh, and then there's one down here. I'm not good at drawing this stuff, so yeah, it looks something like that. And then the spaceship is somewhere located over here. So that's my basically my Alcubierre space-time. So what is the actual metric? So the line element is actually a bit long to express, but the general form is something like this. So ds squared. So we're considering an ADM space-time given by this metric, a squared minus beta I. So I'm writing this in covariant form. These are components, okay? Dt squared. And of course, we're still employing the Einstein summation convention. So plus 2 beta I dxi dt plus gamma I ij dx I dxj. So you'll notice that this general form is not like the Schwarzschild form of the metric, because this is in a much more general space-time, and it's actually quadratic form over here because you'll see the dt squared, and we still have to expand some metrics, so we have to consider some metric. So this is a metric over here, gamma ij. So what Alcubierre studied, so the form that he studied was the following. So alpha is set to 1. So this is actually the lapse function. So you could say, what you can think of is that it's the way that clocks tick in the between these hypersurfaces. So basically they tick at 1 unit every time. And then so yeah, that's why he did that. And then the next thing was B over here. These are the shift vectors between those hyperspaces. So shift vectors are basically like if I parallel transport my vectors, but in a much higher dimensional sense. So basically we're shifting vectors from one hypersurface to another hypersurface. You could correct me on this if I'm wrong, but this is just my intuition on it. So what he said was, okay, I'm gonna let my bx, or well, my first component of my shift vector, which is usually a 4 vector, I believe, I will let that be minus vs of t times f of r s p. So right off the bat, we have three other functions that we want to define, which I will do in a second. So the y component of my shift vector, which is beta 2, is given by, is actually the same as beta 3, or my z component of my shift vector. So beta 3 is 0, basically. So what we're saying by the shift vector is that we're essentially just moving in the x and y directions, right? We're not moving up and down, we're just moving in the x and y directions. So as to not complicate the metric. So v of s, v sub st, and f of R, S, T are very long things, so I'm just gonna write them out over here. So V of ST is some velocity vector. D x s of t over dt, and then r s of t is another function that relates this with the, so basically it's the radius of my hypersurface. So I'm just gonna write it in square form, so I don't have to write that radical. So rs of t squared is x minus x s of t squared plus y squared plus z squared. So this is an application of my, circle relations, but with respect to hypersurface. So, or we'd like to say a hyper catboy, which is basically a catboy in higher dimensions. So my f of rst is then this. So it's a bit long. It's tangent, so the hyperbolic tangent function of sigma times rs plus r minus tan h of sigma rs minus r. So that's all over 2 tan h 2 tan h sigma r. So there, those are the parameters that he studied. And if you guys are still confused by this over here, the final form that he studied for the metric is ds squared is vs of t squared f of rst squared minus 1 times dt, all being multiplied to dt squared, minus 2 vs of t f of rs of t dx dt plus dx squared plus dy squared plus dz squared. There. So you notice that this is much more complicated than Minkowski metric, but it's somewhat similar. So this is essentially the metric. You just if you guys want the exact form, you just need to plug in the required or the defined stuff over here. And this last part over here is actually it's basically just a Minkowski metric, but for the 3 vectors. So for the 3 basis vectors, not including time, basically, because my time component is already preoccupied with its own sort of functions based on it. So this metric describes a warping of space-time, a direct warping, not in the sense wherein it warps space and then punches a hole through it, like the Einstein-Rosen bridge. Well, the Einstein-Rosen bridge is useful in the sense wherein we get there immediately. It's literally a portal from one place to another. This here sort of does not require magical gateways to be opened. You just sort of stretch space or fold space to get there. And if you guys have read Dune, perhaps this is a way of describing how the Spacing Guild transferred their highliners, or actually how their highliners traveled from one system to another. They used some application of this metric, or a much more advanced version of this metric. Now the problem with the metric is that in order to actually manipulate space in this manner, we require negative mass. So we need negative mass. So where the heck do we get negative mass? So this is also called exotic matter, and it's actually hard to find them. Yeah. So that's the thing. Yeah. So we need exotic matter to operate both these guys. So we're still discussing in the theoretical sense. So there's no way that I can actually reuse or misuse a catboy to induce this kind of curvature. However, you could still try to achieve propulsion in space via just a simple application of the Schwarzschild metric. So remember that every time you have an astronomical object in space, it always induces some curvature in space time, or at least not in the sense that we understand it, or not in the sense that we can visualize it via these wells. These wells are very inaccurate, a very inaccurate but simple way of expressing these metrics. But really, we don't have the full picture at the moment because space time bends in a higher dimension. We cannot see it. We can't see it bending. Whenever I drop my pen on the floor, you cannot see that space around it is bending and then it's forcing it to go downwards, right? Because these effects carry on into the time dimension. And I'm not saying that time is a dimension in the sense wherein it is a spatial dimension, but time is some dimension wherein change happens. So without time, we are just stationary, basically. And if you guys have seen some of those diagrams of an apple falling, basically, or maybe just a femboy falling from a tree, sorry for that femboy that fell off the tree, but you'll notice that as he goes down, as we travel through time. So this is my space-time diagram. So x and this is my t. You notice that he goes like this. But at every instant, every slice of time, what we get is a height, basically. And what we're essentially saying with this diagram is that he goes down at every slice of time that we perceive. So he is falling, and then here it's falling, it's falling, it's falling, 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 and falling until it hits the ground. And it's only every slice of time successively that we perceive, basically. So that's really it for this lecture. I'm sorry it's not that long, but there's nothing really much to discuss in the way of the Alcubierre metric. While it is a very interesting construct, it's the same as the Einstein-Rosen bridge, wherein we do hit a wall in terms of using or requiring exotic matter to actually do these contractions of space-time. So this is the Alcubierre metric. And the other one over here, of course, if you want a less spherically symmetric solution to the Einstein Field Equations for Catboys, of course, I have my Levi-Civita space-time. And so that's it for this lecture.